In this video, we will be focusing on how to optimize revenue. So the questions you're going to see in this video are very familiar from grade 10, but we're going to add a derivative twist and slightly tweak our revenue equation. So let's start with our first example. A 150 room hotel will rent all of its rooms if it charges $40 per room. From experience, the manager knows that for every $2 increase per room, 3 fewer rooms will be rented per night. What rent will maximize the revenue per night? So here's what we know. The starting price is $40. And at this price, we're going to get 150 rooms. Every time we increase the price by $2, the number of rooms drops by 3. So we need to find that happy spot where the price is large enough that we still get enough room rentals that will maximize our revenue. Now, revenue is the amount of money coming in. So it's going to be price times quantity, which in this case, the price for the room times the number of rooms that are rented out. So I'm going to start off by creating a few let statements. I need a variable for the price. I need a variable for the number of hotel rooms. So I'm going to say let P represent price. Let maybe N represent number of hotel rooms. So then our revenue is going to equal the price times the number of hotel rooms. Now, how can I come up with an equation for price and hotel rooms? Well, I'm going to add one more let statement, and this is one that you would have seen in grade 10, and that's let X represent the number of price increases. So that way, I can say that price is equal to, well, it starts off at $40 and it's going to increase by 2x times. So if I increase the price 10 times, I'm adding 20 on to the price. And the number of hotel rooms starts off at 150, but we lose 3 rooms for X number of increases. So if I increase the price 10 times, I'm losing 30 rentals. Now, I want my revenue equation to be in terms of that price because it says what rent will maximize the revenue. So I want my equation to be about rent in terms of price based on what's given to me. That way, once I find my derivative and do calculations, I'll just have a more efficient equation to deal with. So I have no problem putting P, but I need an expression for N in terms of P. And if I look at my N equation right now, that represents the number of hotel rooms, it's about X. But if I look at this equation here, I can isolate for X to get it in terms of P. And then I can take that and sub it in here. So let's see what that's going to look like. I'm going to bring the 40 over. And I'm going to divide both sides by 2. So that'll give me half P minus 20 for X. This will allow me to take this expression and sub it in for X, so that way I can write the number of hotel rooms in terms of P. So I'm going to just clean this up. I'm going to distribute that 3 in. So that's 3 over 2P and then plus 60. I'll just collect my like terms. And there we are. Now I have a nice expression about the number of hotel rooms in terms of the price. And I will go ahead and put that into my revenue equation. And now we have an equation for the revenue in terms of price, because the question did ask for what is the rent that will maximize that revenue. Now, before I go and take the derivative of this revenue equation, I want to think about restrictions for a little bit. So I need to put a restriction on P because that's what our equation is about. So let's think about the smallest number that the price is allowed to be. Well, our initial setup is about $40 per room. And the question does say that we're increasing the price, but sometimes we can decrease the price. However, the hotel has 150 rooms. So if I were to decrease the price, that would result in more rentals or more demand for rentals, but we don't have enough rooms. So the lowest the price can be is 40, and we can include that value. But what about the highest the price can be? At some point, the price is going to get so large that no one's going to rent a hotel room. So I need the number of hotel rooms to be greater than 0. So I'm going to go here in this little equation, and I need n to be greater than 0. So I'm going to put this portion, because that's what n is equal to, and say greater than 0. And now I'm just going to isolate for p. I'll multiply by 2 over 3, and I get 140. The price has to be less than 140. And there we are. Now, in reality, I can have 0 rentals, so I did include it in my calculation, so I can make it greater than or equal to. And there we are. So now let's go ahead to the typical finding the derivative, getting those critical points, and doing our test values. At this point, it is repetitive. Now I am just going to distribute p in before I get my derivative. It's a quick distribution. And now my derivative is equal to 210 minus 3 over 2 times 2, so 3p. I'll set that equal to 0. And divide out the 3. And I get a price of 70. So let's test. I'm going to test my revenue when my price is the original 40. I'm going to test my revenue for my critical point of $70 per room. And I'm going to test it at $140. So for that original price of $40, it would just be 40 times 150. That's 6,000. You can, of course, plug in here or here as well. When I plug in 70 into one of those equations, so 210 times 70 minus 3 over 2 times 70 squared, I get $7,350. And when I plug in 140, I get $0. We're trying to maximize revenue, so here it is. So I'm going to write my therefore. Therefore, the hotel should charge $70 per room to maximize revenue. So, just to recap here, we found our revenue equation by doing price times the number of hotel rooms. Now, I wrote individual equations for price and number of hotel rooms, but I wanted my revenue equation to be all about price, all in terms of P, not in terms of X, not in terms of N, and I chose it in terms of the price because we were trying to maximize the revenue and we were asked to find what rent would do that. So I couldn't just plug in this N value, 150 minus 3x, into my equation. Otherwise, I would still have two variables, price and the number of price increases. So I isolated for X in my price equation, then subbed that into my hotel room equation, and then I was able to get the number of hotel rooms in terms of the price. And then off we went to get our equation, our derivative, and our critical point. Our restriction came from partly from the word problem itself, partly from our equation for the number of hotel rooms. The lowest the price could be was 40 because we don't have enough hotel rooms to drop the price and increase that demand. And the highest the price could be would result in the number of hotel rooms being 0. So I created this little inequality saying that the number of hotel rooms had to be greater than or equal to 0, isolated for P, and I got that P has to be less than or equal to 140. And then we were able to do our test values. And there it is. So let's try one more example. A bakery notices when they sell their specialty donut for $6, they will have roughly 200 sales per day. If they decrease their price by 10 cents, they notice that they will have 5 extra sales. Let me write that out. So I start with $6 and 200 sales. If I decrease by 10 cents, so by $0.1, I increase by 5 sales. How much should they sell their donuts for to maximize revenue? Keeping in mind that the most donuts they can make per day is 300. So again, I am looking for that price. So I need to come up with an equation for revenue in terms of price. So my revenue is going to be price times quantity. In this case, donuts. So I'm going to say, again, let P represent price. Let N represent number of donuts, or we could use D for donuts. So here we are, P times N. And I need to come up with those little side note equations for price and donuts. So I'm going to add let X represent number of price decreases. So that way, my price starts off at $6 and we drop the price, so subtract 0.1 X times. And the number of donuts, we start with 200 and we add 5 donut sales every time we decrease the price. So I'm not ready to sub this in for N right here. Otherwise, I would have an equation about P and X. So I'm going to isolate for X in my price equation. So I'm going to do a little bit of swapping here. And I'm going to divide by 0.1. That would get me to 60 minus 10p. Now I can take this X value and sub it in to X in the N equation, which represents the number of donuts. Right now our equation is about the number of donuts in terms of how many price increases, but the minute I do the substitution, now it's about the number of donuts in terms of the price itself, which is what we're trying to get. So that's going to give us 500 minus 50p. And now I'm ready to go into my revenue equation and write it all in terms of price. The revenue is going to equal the price times the number of donuts, but we now have a nice equation for the number of donuts in terms of the price. So that's going to be ready to go. I'm just going to do a quick expanding here to make my life easier, so I don't have to do a product rule. And I'm also going to write my restrictions. So what can my price be? The question doesn't tell me anything about the minimum price or the minimum number of donuts they have to sell. They do give me a maximum. So my restriction is actually going to come from N, and we're going to solve for P for the price in each case. My 2 criteria are as follows. The number of donuts has to be greater than or equal to 0. I can't sell a negative number of donuts. And N has to be less than or equal to 300 because that's all they can make per day. So now that I have this, I'm going to sub this into these inequalities because I'm trying to create my restriction for P because my equation is all about P. So 500 minus 50p has to be greater than or equal to 0. So I'm going to bring the negative 50p over, divide by 50, and I get that price has to be less than or equal to 10. Okay, so I have my upper limit. For my lower limit, n, so 500 minus 50p, has to be less than or equal to 300. I'm going to do some rearranging here, divide by 50, and I get that my price has to be greater than or equal to 4. So we will use these as our test values when we're ready. But now we have our restrictions. Let's get going with that derivative. So our derivative is nice and quick. It's going to be 500 minus 100p. Let's get that critical point. Set the derivative equal to 0. Bring the p term over. Divide by 100. And we get 5 for the price. So that's our critical point. We do have to test. Maybe the best price is 4 or 10. So I'm going to test revenue at 4, revenue at 5, and revenue at 10. And I'm plugging my test values. I'm going to plug them in here. So when I plug in 4, I get 1,200. Not bad. When I plug in 5, my critical point, I get 1,250. So that's better. And if I plug in 10, I get 0. Because if I charge that much, I'm not getting any sales. So our winner is the critical point. So therefore, the bakery should charge $5 per donut to maximize revenue. And there we go. There are some examples for our typical revenue questions from grade 10, but with that derivative twist and a little twist on creating the equation so that it's a little bit more meaningful in terms of the specifics in the question that is being asked.